Hello everyone, my name is Kalyani Sangpal and my topic name is Instrumentation of Gas Chromatography. So let us understand what actually chromatography is. Chromatography is a process for separating components of a mixture. To get the process started, the mixture is dissolved in a substance called mobile phase which carries it through a second substance called the stationary phase. So now we're going to learn about instrumentation part of gas chromatography. First, let us see what is gas chromatography. Gas chromatography differs from other forms of chromatography in that the mobile phase is a gas and the other components are separated as vapors. It is thus used to separate and detect small molecular weight compounds in the gas phase. The sample is either a gas or a liquid that is vaporized in the injection port. The mobile phase for gas chromatography is a carrier gas, typically helium, because of its low molecular weight and being chemically inert. The pressure is applied and the mobile phase moves the analyte through the column. The separation is accomplished using a column coated with the stationary phase. So there are two types of gas chromatography. First one is gas-solid chromatography, in which stationary phase is solid. The other one is gas-liquid chromatography, in which the stationary phase is immobilized liquid. Now let us learn about principle of gas chromatography. The principle of separation in gas chromatography is partition. The mixture of component to be separated is converted to vapor and mixed with gaseous mobile phase. The component which is more soluble in stationary phase travels slower and eluted later. The component which is less soluble in stationary phase travels faster and eluted out first. No two components have same partition coefficient condition, so the components are separated according to their partition coefficient. Partition coefficient is the ratio of solubility of a substance distributed between two immiscible liquids at a constant temperature. So, here is the instrumentation part of the gas chromatography, in which the primary component is always carrier gas. Then sample injection port, third one is column, and fourth one is detector. Detectors used are thermal conductivity detector, electron capture detector, flame ionization detector, and flame photometric. Now let us see about instrumentation part. The first one is carrier gas. In this, helium, nitrogen, hydrogen, argon are used as carrier gases. Helium is preferred for thermal conductivity detectors because of its high thermal conductivity relative to that of most organic vapors. Nitrogen is preferable when a large consumption of carrier gas is employed. Carrier gas from the tank passes through a toggle valve, a flow meter which is 1 to 1000 ml per minute, capillary restrictors and a pressure gauge that is 1 to 4 atmosphere. Flow rate is adjusted by means of a needle valve mounted on the base of the flow meter and controlled by capillary restrictors. The operating efficiency of the gas chromatograph is directly dependent on the maintenance of constant gas flow. Now second part is sample injection system. Sampling unit or injection port is attached to the column head. Since the sample should be in vaporized state, the injection port is provided with an oven that helps to maintain its temperature at about 20 to 500 degrees Celsius above the boiling point of the sample. Gaseous sample may be introduced by use of a gas tight hypodermic needle of 0.5 to 10 ml capacity. For liquid samples, micro syringe of 0.1 to 100 microliter capacity may be used. So injection of samples into capillary columns. So there are four types. The first one is split injection. It splits the volume of sample stream into two unequal flows by means of a needle valve and allow the other smaller flow to pass on the columns, and the bigger part is allowed to be vented to the atmosphere. This technique is not suitable when highest sensitivity is required. The second one is splitless injectors. They allow all of the samples to pass to the column for loading. Samples should be very dilute to avoid overloading of the column, and a high capacity column such as SCOT or heavily coated WCOT column should be used. On column injectors, a syringe with a very fine quartz needle is used. Air cooled to minus 200 degrees Celsius below the boiling point of the sample. After then, the warmer air is circulated to vaporize the sample. Automatic injectors. For improving the reproducibility, and if a large number of samples are to be analyzed or operation is required without an attendant, automatic injectors are used. The solid samples are introduced as a solution or in a sealed glass ampoule crushed in a gas stream with the help of a gas-tight plunger, and the sample gets vaporized and flows into column under the influence of a carrier gas. Now, the most important and you can say the heart of the gas chromatography is the separation column. Columns are of different shapes and sizes that includes U-tube type or coil helix type. They are mainly made of copper, stainless steel, aluminium, glass, nylon and other synthetic plastic. Support material. Its main function is to provide mechanical support to the liquid phase. An ideal support should have a large surface area, chemically inert, should get uniformly weight with liquid phase, should be thermostable. Commonly used solid phases are diatomaceous earth or kissel agar, glass base, polar polymers, sand, etc. Now fourth part is liquid phases. An infinite variety of liquid phases are available limited only by their volatility, thermal stability and ability to weight the support. No single phase will serve for all separation problems at all temperature. Non-polar, in which paraffin, squalane, silicone greases, epizone L, silicone gum rubber, these materials separate the components in order of their boiling points. Second one is intermediate polarity. These materials contain a polar or polarizable group on a long non-polar skeleton which can dissolve both polar and non-polar solids. Example, diethyl hexyl phthalate is used for the separation of high boiling alcohols. Third one is polar. Carboxyls, liquid phases with a large proportion of polar groups. Separation of polar and non-polar substances. Hydrogen bonding. Polar liquid phases with high hydrogen bonding, example glycol. Specific purpose phases. Relying on a chemical reaction with solute to achieve separations, example AgNO3 in glycol separates unsaturated hydrocarbons. Now what are the types of columns? So there are two types. First one is packed columns. So you can see the first two pictures which shows the packed column. In GLC, they are densely packed with finely divided, inert, solid support material, diatomaceous earth, coated with liquid stationary phase. In GSC, the columns are packed with adsorbent or porous polymers. Length is 1.5 to 10 meter. Internal diameter is 2 to 4 millimeter. Second one is capillary column. That length ranges from 10 to 100 meter and inner diameter is usually 0.1 to 0.5 millimeter. It is mainly of two types. First is wall coated column, consists of a capillary tube whose walls are coated with liquid stationary phase, and second one is support coated columns. The inner wall of the capillary is lined with a thin layer of support material such as diatomaceous earth, onto which the stationary phase has been adsorbed. It is also known as plot, that is porous layer open tubular columns. SCOT columns are generally less efficient than WCOT columns. Both typically types of capillary columns are more efficient than packed columns. Now column temperature, which is most important in the instrumentation part. This can be controlled by jacket equipped with vapors of a boiling liquid, electrically heated metal blocks or circulated air baths. Compounds of low boiling point eluted at lower temperature. Compounds of high boiling point boils at higher temperature, resulting in broader and shallower peaks require temperature programming. Detector. Detector sends the arrival of the separated components and provide a signal. These are either concentration dependent or mass dependent. The detector should be close to the column exit and the correct temperature to prevent decomposition. So there are four types of detector. We're gonna see it. First one is thermal conductivity detector. It is based upon the fact that the heat lost from a filament depends upon the thermal conductivity of the stream of surrounding gas as well as its specific heat. When only carrier gas flows, heat loss to metal block is constant, filament T remains constant. When an analyzed species flows past the filament, generally thermal conductivity changes, thus resistance changes, which is sensed by Wheatstone bridge arrangement. The imbalance between control and sample filament temperature is measured and a signal is recorded. Its advantages are simple and inexpensive, durable and possess long life, accurate results, non-selective, hence known as universal detector. And disadvantages are low sensitivity, affected by fluctuation in temperature and flow rate. The second one is electron capture detector. Molecules of compounds which possess affinity for electrons differ in their electron absorbing capacities. This difference is utilized in this detector for identification of the compounds. Its advantages are highly selective, highly sensitive for the detection of compounds like halogens, quinones, peroxides, nitrides, etc. It is non-destructive, more sensitive than TCD and FID. Its disadvantages are least sensitive compounds whose molecules have negligible affinity for electrons, and carrier gas use should be of pure form like pure nitrogen. The third one is flame ionization detector. This employs hydrogen flame that is maintained in a small cylindrical jet made up of platinum or quartz. Effluent from the column with helium or nitrogen as carrier gas are fed into the hydrogen flame, gets ignited and undergoes pyrolysis to produce ions. For detection of these ions, two electrodes are used that provides a potential difference. The ions produced are repelled by the positive electrode which hit the collector plate. The current produced in doing so is amplified and fed to an appropriate recorder. Fourth and the last one is flame photometric detector. It is a selective detector that is responsive to compounds containing sulfur or phosphorus. The detection principle is the formation of excited sulfur and excited hydrogen phosphorus oxide species in a reducing flame. A photomultiplier tube measures the characteristic chemiluminescent emission from this species. The optical filter can be changed to allow the photomultiplier to give light of 394 nanometer for sulfur measurement or 526 nanometer for phosphorus. Flame photometric detector applications are for detection of heavy metals like chromium, selenium, tin, etc. in organometallic compounds. Also for analysis of pesticides, coal, hydrogenated products as well as air and water pollutants. Now the last part of the instrumentation is recorder. The recorder should be generally 10 mV full scale fitted with a fast response pen. The recorder should be connected with a series of good quality resistances connected across the input to attenuate the large signals. An integrator may be a good addition. Conclusion. Instrumentation for gas chromatography comprises well-defined components, each of which contributes to the overall chromatographic performance. Most of these components have reached a mature level of technical development after nearly 50 years of development. Nonetheless, advances are occurring in an evolutionary, not revolutionary manner with sample handling and in refinements of detectors. One area of dramatic advance in GC instrumentation is the development of small sophisticated portable gas chromatograph. Each component of a gas chromatograph, that is columns expected, is discussed below where principles and recent developments are emphasized. Thank you.